Okay, so today we're going to start Unit 7. We're skipping 7.1, so we're just going straight into 7.2 because 7.1 is like a review of very easy concepts that you do in 7th grade that we're not going to worry about. So for 7.2, we have 3 vocabulary. First vocabulary is collinear points. Collinear points are points that lie on the same line. So for example, if I have a line, and make sure you put the arrows, and we'll define a line in just a second, but lines go on forever and ever, so you put arrows at the ends. And I have 3 points on the line, A, B, and C. We would say that A, B, and C are collinear points, meaning they lie on the same line. Okay? Which should just make sense in general. Okay? We also have what's called coplanar. And coplanar are points and lines that are on the same plane. That lie on the same . So when we get into the notes, we're going to talk about points, lines, and planes to start. A plane is, just really quick before we write it down, is a flat surface that has no end and no thickness and goes on forever and ever and ever, and points and lines can be on a plane. So that's why we say points and lines. When you draw a plane in geometry, it looks like a parallelogram to represent that it's a flat surface going on forever. A plane is similar to like the floor, and you guys are the points, and the lines that match you to somebody else is the line. So on a plane, you can have lines that run through it or that lie on it, but we can also have points on the line. You can have points just on the plane, not on the line. And let's name this line L. So we use a cursive L. So we would say that line L and point B are coplanar. We could say that point A and point B are coplanar. So coplanar means that points and or lines that are on the same plane. Okay. Is this familiar to you guys at all? Points, lines, and planes? It's all brand new? Okay, so we're going to define those things in just a second, but I want to get through this first. The last definition that we have is a postulate. So in math, when you are creating new rules for math, order of operations, addition and subtraction, all of our commutative, associative, distributive properties, you have to prove it mathematically. So when I was in college, I got my degree in math, and most of the classes that I took were proving statements or proving mathematical concepts. And sometimes proofs can take pages and pages, sometimes they can be really short. But we need specific rules to help us prove the statements we are trying to prove true or false. And we use what are called theorems and postulates. Have you guys heard of the Pythagorean theorem? At least heard of it? Okay, theorem is a rule that you can prove. A postulate, which is what we're mostly working with right now, is an accepted statement of fact. I don't have an example for that and it's going to be the only one we don't have an example for, but an accepted statement of fact. So it's something that we assume as mathematicians is true, and we just kind of accept that it's a true statement. Okay? Okay, so let's get on to the actual notes, and I'm going to cover some of this up so that it's not super overwhelming. There was going to be a lot of writing in here, guys, and I decided to just give you some of it so that you didn't have to write all of it. You're welcome. So what we're going to talk about first are points, lines, and planes. Okay? Points, lines, and planes. I want you guys to pay attention to the bottom right here first. Points, lines, and planes are called undefined terms. So the top of the box says undefined terms. And then the reason why is down here. So we're going to read that first. These terms are not defined because their definition would require terms that also need defining. So basically, when we're defining a point, a line, and a plane, there are too many terms in the definitions that require further definition. Does that make sense? Like a recursive formula, you can't find term 5 until you know what term 4 is, until you know what term 3 is, until you know, so you have to go backwards. So when we're defining points, lines, and planes, parts of the definition also have to be defined. So mathematically, we just call these undefined terms, and we accept their definitions as they are. Okay? We can use points, lines, and planes to define other terms. So we can use these terms to define further terms. It's all very theoretical. I just have to say it. So we're going to use points, lines, and planes in the definition of other terms. So points, lines, and planes are kind of our basis starting ground. So let's talk about points. A point indicates location. So just like on an XY axis, when you put a point, you're giving me a location, right? It has an X coordinate and a Y coordinate. So we can define its location. But a point has no size. So if I draw on a graph a teeny little pinpoint, like barely noticeable, and Sienna draws a nice big round one, they still indicate the same location. The size does not matter. So we say that points have no size. How we name points. You can represent a point by a dot. So I'm going to underline that. So we draw a dot. So in our diagram, we're just going to draw a dot. And you name it by a capital letter, such as capital A. So all points have a dot and are named using a capital letter. So far, so good? Nothing you don't know? Okay. We also know about lines, right? So lines are represented by a straight path that extends in two opposite directions. And I'm going to underline opposite. So meaning they go in two opposite directions straight, without end, and have no thickness. So same thing. Lines go on forever and ever. That's why we draw arrows at the ends of them. Lines also have no thickness. So drawing a really, really thin line or making the line thicker does not make a difference. It's still the exact same line. So we don't measure thickness on lines. And then a line contains infinitely many points, which is something we've talked about before, right? You do not have to put a point just on the integers. You can put a point anywhere on the line. And there are infinitely many of them. So how do we name it? We can name a line by any 2 points on the line. So we could take 2 points on the line, let's call them A and B, and draw a line through them. So if we are naming a line by 2 points on the line, we call it line AB, and we use this notation. AB, capital AB with a little line over it, and I want you guys to pay very close attention. The little line above it has arrows on the ends, right? Okay, that's important. Have you guys done this before? Okay, so if it doesn't have the arrows, it's called a line segment. So you have to have the arrows on the end because a segment and a line are two different things. You can also flip-flop the letters. So you can also call it BA with the line over it. And please make sure you put the arrows. Lines can also be named by a single lowercase letter, such as line L. And if you're going to use L's, I suggest doing a cursive L. You can also name lines M, N, whatever you want, but we name lines with lowercase letters. We name points with uppercase letters. Okay, so we can say line L, or we could call this line AB or line BA. So far, so good? Am I overwhelming you yet? Okay. Planes should be totally new, right? Okay. A plane spelled P-L-A-N-E, so not like like an airplane, not like a plain bagel. A plane is represented by a flat surface. So like a piece of paper that extends without end, and has no thickness. So same as a line, it has no thickness, it's just flat. And it's a flat surface that goes on forever and ever. A plane contains infinitely many lines. And if lines contain infinitely many points, does that mean a plane also contains infinitely many points? Right? Logical thinking, guys. If a plane has infinitely many lines, and a line has infinitely many points, a plane also has infinitely many points, right? Okay. So when we draw a plane, I'm going to draw it first, then we'll talk about how we name it. We draw it in a parallelogram shape to indicate that it's not a square or, that it's not just like a square geometrical figure. And that also kind of means we're going off in all kinds of directions. And we can name it by a capital letter, such as plane P, and when we do that, we put the capital letter in the corner of the plane, and we don't put a point next to it. Okay, so that's the difference. If you're naming a point, it has a dot next to it. If you're naming the plane, there's no dot next to it, but it's still a capital letter. Another way that you can name a plane is by 3 points on the plane that do not lie on the same line. So 3 points that are not collinear. For example, point A, point B, and point C. Do these 3 points lie on the same line? They don't all line up, right? So we can name the plane A, B, C. Okay, so you would write the word plane and then write the capital letters A, B, C. The order doesn't matter, just like on a line. Okay, so far so good? Okay, we're going to practice just naming. So, because this is super important. So you guys have to make sure you're getting the names correct before we can move on to anything else. So the next 8 questions, I give you, on the first 4, I give you a plane with some stuff on it. And on the second 4, I give you a new plane with some stuff on it, and you're going to name them. There's one thing I want to point out to you, and we're going to do the first 4 together. What do you guys, when you're looking at this picture, let me zoom in. I want you to notice, look at line L. So the line that has the points R, Q, and S. It's a solid line, right? Do you guys see that? That means that the line lies flat on the plane. So if this piece of paper was my plane, do you see how I drew a line on it? Everybody see the line? That means it's like the line is drawn on the plane. But look at the other line, the line that contains points T, Q, and N, or line M. What do you notice about that line? Look very carefully.
It's a segment.
It's not a segment because it has arrows at the end, but do you guys see that dotted part right here? That means that the line is going through the plane. So for example, if my pen was the line, if I could cut a hole in it, that means that my line is going right through the plane. So does that line lie on the plane? No, because it's going through it. Does that make sense? Okay, so in geometry, it's really difficult when you're doing problems on paper because they're more three-dimensional looking. So we indicate that by a dotted line. So line L lies on the plane because it's solid, so it's flat on the plane, right? But line M has the dotted line, which means it's going through the plane, okay? So it does not lie on the plane. Therefore, the points on it do not lie on the plane. Make sense? We'll do this one together, okay? So let's talk about number 1. What are 2 other ways to name line QT? So line QT is the one that's going through the plane because it has the points Q and T on it. I noticed that it has a lowercase letter m, so we could call it line M, right? You guys agree? Okay, so I'm going to call it line M. And then we need to name it also using other points on the line. So what are other ways that we could name line QT? What are some other points on line QT? What do you guys think? TQ. Could I do TQ? Just flip-flop the letters? Yep, so we could do line. So you draw your line above it. TQ. That works. Can I use the point N to name the line? I can, because it's on the line, right? Even though this line is not on the plane, it's still a line. So I could also use, say, line TN. So I could call it TN because the line goes through the points T and N. What about line NT? Could I use line NT? Okay. What about QN? Could I use Q and N? Yep. What about NQ? Yeah, there's a whole bunch. I'm going to use QN also. So just to give you some options. So there's a whole bunch of ways you can rename lines. You can use any points on the line to name it. What about number 2? What are 2 other ways to name plane P? So notice how this whole plane is plane P. What are ways that we can name planes? What did our definition say? How many points do we need? 3. Can they be collinear? No. So it already named the plane with a letter, so we can't use that. So let's look for 3 points that are not collinear. I see point V on the plane. R is on the plane, and Q is on the plane. So we could do QVR. Is there any other points on the plane that we could use? David?
RVS.
RVS. Yep, we can do that too. So we could say plane RVS. Could I use the name plane RQS? Does that work? Why? They're all on the same line. Could I use the point T to name the plane? No, it's not on the plane. What about point N? Not on the plane either. Is this making sense? Okay. So then we kind of already answered our own question. What are the names of 3 collinear points? What are the points that are collinear here? RQS. Do you see any other collinear points? What about on this line? What 3 points lie on that line? TQN. So RQ and S are collinear, and TQ and N are collinear. Okay. And then the last one, what are the names of 4 coplanar points? There are only 4 coplanar points on here. What are the 4 points on the plane? P is not a point. P is the name of the plane. So R, Q, S, and V. Q, R, S, and V. Not too bad? Okay. So what I'm going to have you guys do, I want to make sure we have enough time. So I'm going to give you just a couple minutes. You can work with your neighbor. Do problems 5, 6, 7, and 8 for me. On this one, I want you to notice, look at line M. Does line M have any dotted sections to it? No. So that means that line M does lie on the plane. Okay? So line M is lying flat on the plane. It's just showing us that line M extends forever. But because it's a solid line, that means it is on the plane. Okay? It's just like as if I was to draw it with a permanent marker on there. So I'm just going to give you a couple minutes to rename the points on there. Okay, I'm just going to give you guys some of my answers. What are two other ways to name line BE? So BE, we could call it line N. So hopefully you use line N. We could also call it line EB if we wanted to. So we could just rearrange the letters. But we could also use point F. So we could call it point BF. Or we could use EF as well. So any 2 points on the line you can use. And then for BF and EF, you could also flip-flop those. Two other ways to name plane C. So to name planes, you have to use either the capital letter that's given or 3 non-collinear points. So non-collinear points would be E, G, and B. Or you could have called it plane BGF. Or you could have used, that's it, right? No, EGF. You could have also used plane EGF. Okay, so any of those work to rename the plane. You cannot use EBF because they are collinear. The names of 3 collinear points would be E, B, and F. And those are the only ones because they didn't give us any other points on line M. And what are the names of 4 coplanar points? There's the 4 points on that plane, E, B, F, G. Okay? So far so good, guys? Okay. So then let's talk about terms that we need the definition of points, lines, and planes for. So those other terms at the bottom. Oh, mine didn't print out. Well, okay. There's my other one. Okay. So, sorry guys. We're going to talk about segments first. So a segment is a part of a line that consists of 2 endpoints. So 2 is where your blank is. And all the points between them. So that means infinitely many points. Okay? So a segment has 2 endpoints and consists of all the points between them. We name a segment similarly to how we name a line, except that we don't by its 2 endpoints. So you can't use any points on the segment. You have to use the 2 endpoints. And when you do the notation, it's just a straight line above the 2 endpoints, no arrows on the ends. And you call it segment AB. Or you can flip-flop them and call them segment BA. And it would look like this in a picture. So you have to use the endpoints when you're naming a segment. We also have array. Array is part of a line that consists of 1 endpoint and all of the points of the line on one side of the endpoint. So basically, in our picture, you have an endpoint, and then it extends out in one direction, and you have an arrow only on that one direction. You name a ray by its endpoint and another point on the ray. So it's endpoint and another point on the ray. For example, ray AB. And we do the notation of a ray with one arrow going to the right. So one confusion that students have when they're naming rays is they put the arrow above the points going whichever direction the ray is going. When we write it out, we always use to the right to indicate a ray, okay? We tell the direction by the order in which we order the points. So AB means that the endpoint is on A and then I'm going in the direction of B. Does that make sense? If I were to name a ray, ray BA, so here, let's do this. Ray AB would look like this, an endpoint at A, and then it's going in this direction towards B. That's what it would look like. If I were to name ray BA, that means my endpoint is at B, and the ray is going in the direction of point A. Does that make sense? So whichever letter comes first tells us where the endpoint is, and then whichever letter comes second tells us the direction. But in both notations, you use the arrow going to the right, okay, for the notation. So because we have rays, we also have what are called opposite rays, which is pretty self-explanatory. Opposite rays are two rays, so that's your blank, that share the same endpoint and form a line. So it's a line, but we break them up into rays. So you can name opposite rays by their shared endpoint and any other point on each ray. So in this picture, we have ray CA, so one ray going in this direction, and its opposite ray is ray CB, going in the other direction. Okay, so those are the two opposites. Don't write down the answers, unless you already did. Okay. I'll cover it. So much better not having to do so much writing. I thought so. Okay, so let's look at the examples. Am I good? Can I move it? Is everybody done writing? Okay. So the examples for this one. What are the names of the segments in the figure? So I give you this figure. It has, it's a line and it contains the points D, E, and F. There's several segments on here, so we're going to try and name them all. The first one is there's a segment DE, right? Going from D to E. And we call that, just put the straight line over it. So there's segment DE. Can we flip-flop those two? Yeah, so there's also segment ED. Same segment. Another one that I see is DF, so we can do segment DF. And we can flip that and call it segment FD if we want. They're the same segment. And then what's the other one that we're missing? EF. So we also have segment EF, and we can flip that and call it segment FE. I think that's all of them. Okay. So number 10 says, what are the names of the rays in the figure? There is a ray going from D to E, so from D through E, so we can call it ray DE. What's the other ray that has endpoint D? So what's the other ray that we can say with endpoint D? D what? DF, good. So ray DF. We also could use E as an endpoint, so we could have E going through F, so we could have ray EF. And what's the other ray with endpoint E? ED, so it's going in the opposite direction. So there's also ray ED, but when we do the notation, it looks exactly the same. The endpoint is what tells us the direction. And there are two rays using F as an endpoint, ray FE and ray FD. Ray FE and ray FD are the same ray, we're just naming it using different points, and the same thing with DE and DF. It's really the same ray, we're just using a different point to name it. Only two of these rays are considered opposite rays. What are the two opposite rays? Yeah, good. ED, which goes this direction, and EF, which goes this direction. So there's ray ED and ray EF. I know that for some of you this is repetitive, and I know, but there are some of you that have not had this before, so we have to kind of cover both bases. And this is important because when we start getting into all of the stuff we're going to be doing with them, being able to name everything properly is important. Okay, so that's points, lines, planes, rays, and segments. So that's all the basic geometric building blocks. Everything you do with geometry can be done using those building blocks. But what we're going to start talking about now are our postulates. I do not expect you to know that postulate 1 says that through any 2 points there is exactly one line. Some of these postulates are things that you already know or things that just make sense to you. That's why postulates are statements that are just accepted as fact, because logically they reason that it makes sense, it's true. There are some special postulates that have their own names. Not ones that we're going to talk about today, but ones that we will talk about next week. We're not just going to call them postulate 1, postulate 2, postulate 3. There are a couple postulates that have their own special names. Those are the ones that I expect you to know, okay? These ones that have just numbers that we're just numbering off, you need to know the concept, but you do not need to know which one goes with which number. Does that make sense? So I expect that you know that through any 2 points there's exactly one line, but I do not expect you to know that that's postulate 1, okay? So some of these things you might already know as well. One of the basic first things you learn in geometry is that through any 2 points, there is only one line, which should make sense. There's no other way that we can draw a line through points A and B besides the one that's already given, okay? We can also say the converse, or going the opposite direction, that line T is the only line that passes through points A and B. So line T is the only line that can pass through points A and B, okay? So through any 2 points there is one unique line. Postulate 2 is also something that should be pretty intuitive to you. If 2 lines intersect, then they intersect in exactly 1 point. So when 2 lines cross, there's only 1 point where they intersect. We did this already with systems of equations, right? The equation of this line and the equation of this line only has one solution. Okay, if they're parallel, how many solutions do they have? 0. And if they're the exact same line, how many solutions do they have? An infinite. But if they do cross, they can only cross in one place. So we would say that line AE and line BD intersect at point where? In point C. So we say line AE and line BD intersect in point C. So that's where they cross. So far it should not be anything that you don't already know. Postulate 3 should be the new one. So if two lines intersect and they only intersect in one point, it should make sense that if two planes intersect, they intersect in exactly one line. And I created this to show you that. Okay? So we have on this piece of paper that I punched a hole in, plane, the blue plane and the yellow plane. And they intersect. What do you notice about where they intersect? There's a line, which should make sense, right? There's an infinite amount of lines on plane B, and there's an infinite amount of lines on plane Y. So when they intersect at one specific line. The whole line is the intersection because planes go on for how long? Forever and ever. So really this blue plane is going on forever, and so is the yellow plane. And what else do we know goes on forever and ever? Lines. So we would say here that plane RST, because it has the points R, S, and T on it, and plane WTS intersect in what line? Where is the line? What points does the line go through? S and T. So in line ST. Something that students get confused a lot is the line will not always be drawn where they intersect, so they will say that it intersects at the segment. But remember, planes go on forever, and so lines go on forever. Segments do not go on forever. So it can only intersect at the line because the line is what continues forever and ever, just like the planes. Okay? So that's something that you need to make sure you remember. So I always suggest that you draw the line. So remember, these things are going on forever and ever and ever. Just when we draw the picture, we have to end it somewhere. Okay? So let's talk about that right now. 12 and 13, intersection of two planes. So what this cube that I have on the paper, we're going to say that all of the sides actually represent planes. So they are actually going on forever and ever, meaning their intersections also go on forever and ever. So let's look at where these things intersect. What is the intersection of plane ADC? So the plane that contains points A, D, and C would be this plane right here, correct? The top part. And I'm going to use a different color. And the plane BFG, so the plane here, BF and G, which is this plane here, they intersect. Where do they intersect? Do you guys see the corner where they intersect? So right here on this edge, that's where they intersect. So draw the line. So the name of the line where they intersect is line BC or CB. Okay. So you have to make sure you draw it as a line. You cannot name it just the segment. So let's do, now that I drew all over this one, let's do number 13. What are the names of two planes that intersect at line BF? So this line right here. So the two pieces that share that edge are this plane right here. So plane BFG, right? And the plane that intersects on that edge would be this plane right here, because they share the edge. So that would be plane, 3 points on that plane. BFE.
Could you still use A?
You could still use A, so we would have to say plane BEA or plane BFA. You could still use it. So and just like on the purple one, you could also use point C to name the plane, because each of these planes have 4 points on them. So you just pick 3 of them. Okay. These are difficult because it's 3-dimensional figures and it's hard to see it. So the very last one that I want to show you guys. So just like postulate 1, through any 2 points is exactly 1 line. The same thing is for planes. Through any 3 points, there is exactly 1 plane. Okay? 3 non-collinear points. So the 3 points that we use to name a plane, through any 3 points, there's exactly 1 plane. So we would say that points Q, R, and S are non-collinear. Plane P is the only plane that contains them. So basically what this is saying is the exact same thing as postulate 1. If I give you 3 points, there's only 1 plane that contains those 3 unique points. There's no other plane that has those 3 points only. Okay? So the very last thing we're going to do is identify planes that correspond with the points that I give you. So on number 14, what plane contains points N, P, and Q? So I have point N here, point P is here, and point Q is here. So you guys, according to this rectangular prism, what section of it has those 3 points? One of the sides, the top, the bottom, the back, what is it? The bottom. So points N, P, and Q is this bottom section right there. So we're just shading where the plane is to help you visualize it. But of course, I'm not going to make it too easy for you. What plane contains points J, M, and Q? So let's put points where we see them. J, M, and then Q is all the way in that back corner. So where is the plane going to be? Is it that back side? Because point J is on the front. The top doesn't contain point Q. But this side doesn't contain point M. Oh my gosh, what are we going to do? There is. It's the diagonal that goes through the box. So draw with me. A solid line from J to P, and then you're going to visualize it, be able to see it. And a dotted line from N to Q, M to Q, because it's in the back. And that's your plane. So it's like if I had a shoebox or this Kleenex box, the plane is the one that goes through the diagonal.
If you cut it into a ramp.
If you cut it into a ramp. It's like the ramp that goes through the box. Okay, I think there's one like that on your homework, so just so you're aware. Okay, so that's it. I know it's a lot of information. Some of it is brand new, but it's the basis of everything, so it is important. So your homework tonight for the weekend is worksheet 2. I think is it double-sided?
Yeah.
It is? Okay. It's a lot of naming, though. It shouldn't take you too long.